The topic of this video is an introduction to Poisson distribution. A random variable x is called a Poisson random variable with the parameter lambda if the PMF or the probability mass function of x is given by the equation P of k equal to the probability that x is k is equal to e to the negative lambda to the k divided by k factorial, where k is a non-negative integer. Okay, so let me try to give you some examples where Poisson distribution can be used. So in situations where we look at occurrences of rare events, we can apply Poisson distribution. So as examples, some variables that generally obey the Poisson distribution are number one, the number of misprints on a page, a number of people in a community who survive to age 100, number of packages of dog biscuits sold in a particular store each day, the number of customers entering a post office on a given day, number of alpha particles discharged in a fixed period of time from some radioactive materials, and there are many more examples, like the number of patients waiting in the emergency center, number of customers waiting on a line at a ATM booth during a specific period, and so on. We will go back to looking into this the application of random variables in a bit more detail later. So right now let's look at the expectation and variance of x. So assume that x is a Poisson random variable with parameter lambda, or x has Poisson distribution with parameter lambda. Then we have this, number one, we have this recurrence relation for the PMF of x. P of k plus 1 is the same as lambda divided by k plus 1 times P of k, and the expectation of x is lambda, and so is the variance of x. So the first thing I'm going to do now is derive the recurrence relation. So let's derive. So derivation of number one. So in order to derive the recurrence relation, what I'm going to do is look at the ratio of P of k plus 1 and P of k. Now we know that P of k is given by e to the minus lambda to the k divided by k factorial. Now if that's P of k, then what is P of k plus 1? Well, P of k plus 1 would be e to the negative lambda to the k plus 1 over k plus 1 factorial. Clearly e to the negative lambda cancels out, and so the remaining ratio I'm going to write in the following way: lambda to the k k plus 1 over k plus 1 factorial times k factorial over lambda to the k. Again, what I said is we can cancel out the e to the negative lambda. Now we realize the following, that this is equal to, notice that lambda to the k and lambda to the k plus 1 reduces to lambda over 1, and so what I have now is lambda times k factorial divided by, now k plus 1 factorial that I have in the denominator, we will write it as k plus 1 times k factorial, so then we can cancel out k factorial. So finally what I have then is p of k plus 1 over p of k is equal to lambda over k plus 1, and it implies that p of k plus 1 is lambda over k plus 1 times p of k, and so this is the desired recurrence relation for the PMF of the Poisson random variable x. Okay, so that's number one. Okay, now we will try to derive the expectation of x. Okay, so now we look at the derivation of the expectation of x. Well, we know that the expectation of x by definition is the summation over all values of x. So we know that the values of x are the non-negative integers, so k going from 0 to infinity, k times p of k, and we now plug in what p of k is. P of k is e to the minus lambda to the k over k factorial. So notice that this is equal to e to the minus lambda in the sum doesn't depend on k, so we can factor that out. E to the negative lambda is factored out of the sum, and we will, so then what we have is the following. Wait a minute, so one thing I forgot to do here is, okay, if you look at the sum, the sum end corresponding to k equals to 0 is in fact 0. So instead of starting the index at 0, I can start it at 1, and I'm going to do the same thing here. So notice that I have k lambda to the k. In the denominator I have k factorial, which I'm going to write as k times k minus 1 factorial, and then k will cancel out, so then I have the following, e to the minus lambda, so k cancels out. What I'm also going to do is I'm going to factor out lambda, and then the sum will be k going from 1 to infinity lambda to the k minus 1 over k minus 1 factorial. Now I'm going to shift the index of the sum, so I have lambda e to the minus lambda summation. So I'm going to replace k by k plus 1. If I replace k by k plus 1, then the summation will start at 0. And then if I replace k by k plus 1, I get k and then k factorial in the denominator. Now think about what this sum is. Okay, not yet, sorry. What I'm going to do is I am going to now say that the expectation of x is lambda times the summation k going from 0 to infinity e to the minus lambda to the k over k factorial. So the e to the minus lambda that I have outside the sum, I put in the I transferred it in the sum. Now if you think about this sum, now look at the sum end. The sum end is exactly the probability that x is k, right? So basically then this summation is giving you the sum of the probabilities of all the values of x, which is the total probability, and therefore it's got to be 1. So what we get for the expectation of x is that it is lambda times 1, which is lambda. So that gives us the expectation. Now there is another way. There is another way of going from this step. So let me show you that as well. So instead of writing what I wrote here, what I'm going to do is say the following. Well, I have lambda times e to the minus lambda, and now think about this sum. If you remember from calculus, this is exactly the power series representation of e to the lambda. Okay, and now e to the minus lambda and e to the lambda, when we multiply them, we get e to the 0, which is 1, and therefore we end up with lambda as the expectation of x. Okay, so that's the derivation of the expectation. I'm gonna pause for a second. I'm gonna make some room in my notes. Okay, let's derive the variance of x. We know that the variance of x is the second moment expectation of x squared minus the first moment expectation of x, and you take the square of that. I notice that we have already calculated e of x, so now we need to find e of x squared. So let's try and do that. Okay, I don't know why I have that 2 here. Okay, so let's derive that. So the expectation of x squared, by definition, this will be the sum over all values of k, k squared times p of k. Once again, because the sum end corresponding to k equals to 0 is 0, we can start the index at 1, which would be this. Now we plug in what p of k is. So this will be equal to the summation k going from 1 to infinity, k squared. P of k would be e to the minus lambda to the k over k factorial. Now we're going to factor out e to the minus lambda as before, and we have k going from 1 to infinity, k squared, lambda to the k over k times k minus 1 factorial. Notice then we have e to the minus lambda summation k going from 1 up to infinity, k times lambda to the k over k minus 1 factorial. What I'm going to do is I am going to write lambda, I'm going to factor out a lambda and then write lambda to the k minus 1 here. So now I'm going to change the index for the sum. I'm going to replace k by k plus 1. If I do that, I get k going from 0 to infinity, k replace k by k plus 1, lambda to the k, if I replace k by k plus 1, divided by k factorial. I need to make a little bit of more room here. Okay, so this will be equal to lambda times e to the minus lambda summation k going from 0 to infinity. So this summand can be written as, if I multiply out, I get k times lambda to the k over lambda to the k over k factorial plus lambda to the k over k factorial. So I simply multiply it out. So this is what I get. This would be equal to lambda times e to the minus lambda summation k going from 0 to infinity, k times lambda to the k over k factorial plus the summation k going from 0 to infinity, lambda to the k over k factorial. And I better be careful here. Let's put some brackets, curly braces around. Once again, I need to make a little bit more room. Okay, so if you look at the first sum, well, that's familiar because we already had that sum, right? Let's see, where did we have that sum? Well, okay, here's what I'm going to do is I'm going to write one more line, lambda times e to the minus lambda times the summation k going from 0 to infinity, k lambda to the k over k factorial plus the second sum here is the power series representation of e to the lambda, as we seen before. I'm going to multiply out now as lambda times the summation k going from 0 to infinity, and I'm going to put the e to the minus lambda inside the sum not this way, sorry. let me write it this way. I'm going to write k first, and then I'm going to write e to the negative lambda to the k over k factorial plus when I multiply lambda, e to the minus lambda and e to the lambda, I'm going to get lambda. Now notice what this sum is. This sum, if you look back, it is exactly the expectation of x, and we already know that the expectation of x is lambda. So what we get here is lambda times lambda, because that's the well, let me write one more line here. So this is lambda times the expectation of x plus lambda, which is lambda times lambda, we've seen that, plus lambda, which is lambda squared plus lambda. So what we have obtained now is that the expectation of x squared is lambda squared plus lambda. I'm going to make a little bit more room. Okay, so now the variance of x, which is expectation of x squared minus expectation of x squared of that, which is be lambda squared plus lambda, that's the second moment, minus the expectation squared, which gives you lambda again. So the variance of x is lambda. So the expectation is lambda, so is the variance of x. Okay, so that's the end of my introduction, we will cover more on the Poisson distribution in the next video.